Welcome to section 8.5, Parametric Equations. Parametric equations and graphs. Okay, so let's consider a point in the plane x comma y. So if there exists some real number or some t such that x is a function in t and y is also a function g in t, then we can write the point x comma y as f of t comma g of t, where t is the parameter. Okay, so for definition, so a parametric equation, is the set of all points. So is the set of all points x comma y, where both x and y are functions of the parameter t, are functions of a parameter t. Okay, so what do I mean by this? Let's see this in action. So for example, let's plot the following parametric equations. On the given interval for t. So given interval for t. Okay, so number one, let's say we are given that x is 2 times cosine of t and y is 3 times sine of t. And we're told that t is between 0 and 2 pi. Okay, so the way I'm going to do this is I'm going to set up a XY chart, except I'm going to tack on a t. Pardon me. Okay, so how much room do I need? Let's see. So here's my t. I start at 0. And let's go to pi over 2. That's always my favorite. Then pi. And then 3 pi over 2. And then I guess I'll come full circle almost to 2 pi. Can't actually get to 2 pi because it's open, but I can almost get there. Okay, so the x coordinate, which is 2 cosine of t. So cosine, not cotangent. 2 cosine of t. Okay, so cosine of 0 is 1. So this is 2 times 1, which is 2. Cosine of pi over 2 is 0. So this is 2 times 0, which is 0. Cosine of pi is negative 1. So 2 times negative 1 is negative 2. Cosine of 3 pi over 2, oops, move this up a bit. Cosine of 3 pi over 2 is going to be 0, so 2 times 0 is 0. And last but not least, going full circle, 2 pi, because under 2 pi is 1, so we'd be back to where we started. Now let's see y is 3 sine of t. Okay, so at 0, sine of 0 is 0, so 3 times 0 is 0. At pi over 2, sine of pi over 2 is 1, so 3 times 1 is 3. Then at pi, sine of pi is 0. I'd have 0. Then at 3 pi over 2, sine is negative 1, so that's negative 3. And going full circle, at 2 pi, sine is 0. Okay, so let's plot these points on the restricted domain. I know my values for y vary between negative 3 and 3, and my values for x vary between negative 2 and 2. Okay. X and y, let's see if I can make this. Let's do 1, 2, 2, 3. 1, 2, 3. 1, 2, and 3, and 1, 2, and 3. Kind of. Yeah. Okay, so my first point is at 2, 0. That's when t is 0, right? T equals to 0. My second point is at 0, 3. And that is when t is equals to pi over 2. That's interesting because look at where it's oriented, at what angle it's oriented. So at my next is at 0, negative 2, 0. So this is when t is equals to pi. And the next point is at 0, negative 3. And this is when t is equals to 3 pi over 2. And then I come full circle to 2, 0. So what I have is a graph. Maybe I'll do this in orange. That looks something like so. It starts on the x-axis, goes up to the y, then to the negative x, negative y, and then full circle. So what has happened is I have a direction that this goes in as my values of t increase. Okay, so let's do another one. Number 2. Let's say I give you that x is t plus 1 and y is t squared. Let's have t be between negative 2 and 2. So once again, I'm going to do a t x y chart. So let's see, I'll have negative 2, negative 1, 0, 1, and positive 2. So this is how far down I'll go. Okay, so my values for x. So x is t plus 1. So negative 2 plus 1 is negative 1. Then negative 1 plus 1 is 0. Then 0 plus 1 is 1. Then 1 plus 1 is 2. And then finally 2 plus 1 is 3. So those are my values for x. My values for y are t squared. So negative 2 squared is 4. Negative 1 squared is 1. 0 squared is 0. 1 squared is 1, and 2 squared is 4. Okay, so my values for y vary between 0 and 4. My values for x vary between negative 1 and 3. X and y. Let's do 1, 2, 3, 4. Negative 1, and 1, 2, 3. 1, 4. Okay, so my first point is at negative 1, 4. So this is when t is equals to negative 2. My second point is at 0, 1, and that's when t is equal to -1. My third point is at 1, 0, and that is when t is equal to 0. Okay, let me write that 0 a bit better. T is equals to 0. My third point is at, 2, 1, and that's when t is equal to 1. And my last point is at 3, 4. So this is when t is equals to 2. So what's happening is that I start here at -2, and I just have this portion of what looks like a parabola. It induces a direction as t increases. Okay, so that's terrible. Let me try and draw this a bit better. Okay, so the direction has been from -2 all the way to +2. Okay, so what's going on? The parameter induces a direction, so let's note that. So note the parameter t, induces a direction to our graph. So induces a direction to our graph. Okay, so note. So eliminating the parameter can help to identify the graph. So note, eliminating the parameter can help to identify the graph. Hey, little kitty. Okay, so for example, eliminate the parameter. And plot. So be sure to indicate direction. Okay, so number 1, let's say we have that x is secant of t, and let's have y be tangent squared of t, and let's have t be between 0 and pi/2. Okay, so I could do a t/x/y chart, and in fact, why don't I just go ahead and do that so that we have this to fall back on. Pardon me. So I'm between 0 and pi/2, so let's try pi/4, and then pi/3, and then pi/2. I can't actually get there, but I'll put this. So x is secant of t. Okay, so secant of 0, it's a reciprocal to cosine of 0. So that's just 1. Secant of pi/4 is a reciprocal of cosine of pi/4, so that's just the square root of 2. Secant of pi/3, well, that's a reciprocal of cosine of pi/3, so that's 2. And secant of pi/2 does not exist. It's a vertical asymptote. So it approaches positive infinite because cosine is approaching 0. So I'm just going to put dne, which is why we can't include pi over 2. So now let's do the same for y being tangent squared of t. So tangent squared of 0, well, tangent of 0, 0 squared is 0. Tangent squared of pi over 4. Tangent of pi over 4 is 1, 1 squared is 1. Tangent squared of pi over 3, well, tangent of pi over 3 is root 3 squared is 3. And tangent squared of pi over 2, well, does not exist because tangent of pi over 2 doesn't exist. Okay, so what this means. What does this mean? Let's eliminate the parameter now. So let's do as they say. So we know that x, let's see, x is secant of t, and y is tangent squared of t. So do I know of any identity wherein I have both secant and tangent? And I do. It's one of the main 3 Pythagorean identities, namely tangent squared t plus 1 is equal to secant squared t. So since I'd like to solve for y, this becomes y plus 1 is equal to secant squared is x squared, right? So I just get that y is equal to x squared plus 1, which is a parabola shifted up 1 unit. So let's see what happens when I plot this. So x and y coordinate axes. So I know that this is a parabola shifted up 1 unit. 1, 2, 3. 1, 2, 1, 2. Or down rather. Oops, I subtract 1, not add 1. What am I saying? Okay. Minus 1. Sorry. Do as I say, not as I do, clearly. Okay, so down 1. Okay, so normally I would plot the whole thing, but I don't know where this starts. So what I'm going to do is I'm going to look at the first point, which was at 1, 0. So this is when t was 0. The second point is at root 2, 1. So for me, it would be easier. I know that the original parabola would look something like so. Intersect at -1, so it should be something like so. So it'd be 1, 3. Sorry, 2, 3, -2, 3. So this is what the parabola would look like if I were able to draw the whole thing. So the next point, since I don't know where root 2 is, I do know where 1 is on the y-axis, so I'm going to assume it's right here. So this is when t is equal to pi over 4. The next point is at 2, 3, and that's when t is equal to pi over 3. So as t becomes infinite, my values for secant and tangent also become infinite, which means I can draw the whole other part of this parabola, but I cannot draw anything to the left of that orange line. Actually, let me make this dotted look a little bit better. So I'm not allowed to draw the whole parabola is what I'm saying. I'm only allowed that portion that corresponds to the t. Okay, so let's do one more of these. Okay, so number 2. Let's say we're given that x is equal to 3 times cosine of t. And let's have y be equal to 2 times sine of t, where t is between 0 and pi. And let's have this be inclusive. Okay, once again, even though I am telling you not to do this, I want to make sure that we know what we're doing. So let's do a t versus xy chart. So I start at 0, then I'll go to pi over 2 because that's an easy number, and then I'll go to pi. And let's just leave it at that. So x, of course, is 3 cosine t. So my values for x are going to be 3 cosine of 0 is 1, so that's just 3. 3 cosine of pi over 2 is 0, so that's 0. And 3 cosine of pi is negative 1, so that's negative 3. Okay, my values for y are 2 sine of t. Okay, so this is 2 sine of 0, 0, so that's just 0. Sine of pi over 2 is 1, so 2 times 1 is 2. And sine of pi is 0, so that's 2. Okay, but now let's eliminate the parameter. Actually, yeah, let's eliminate the parameter. So we have that x is 3 cosine of t. And we have that y is 2 times sine of t. So the Pythagorean theorem, I know, is going to be cosine squared t plus sine squared t is equal to 1. That's my main Pythagorean identity. Okay, so cosine squared in this case is going to be x over 3 quantity squared. Sine squared in this case is going to be y divided by 2 quantity squared. That's equal to 1. So otherwise known as x squared over 9 plus y squared over 4 is equal to 1. This is the equation of an ellipse, right? An ellipse with center 0, 0, vertical radius a, so or horizontal radius equals to 3, and vertical radius equals to 2. Okay, so let's see if that's what we get. So x and y coordinate axes, I claim that this is an ellipse centered at the origin. Why is it I can never make these even? Do not know what it is. Okay, so 1, 2, 3, 1, 2, 1, 2, 3, 1, 2. So this would be an ellipse centered at 0, 0 with horizontal radius 3 and vertical radius 2. However, I cannot draw the whole ellipse because I'm only allowed to have the ellipse from the first point, which is 3, 0. This is when t is 0. The second point is at 0, 2. So that is when t is pi over 2. And the final point is at negative 3, 0. Oops, 2 times. 2 times 0 is not 2, it's 0. Okay, so my final point is at 0. So this is when t is equal to pi. So actually, I'm only allowed to have the top part of this ellipse, and the direction that t induces is from right to left, or counterclockwise. Okay, and how about we call this a semester? That's it.